5,000-year-old blood evidence doesn't match modern humans. The result didn't make sense the first time they saw it. In fact, it wasn't even supposed to be possible. A preserved blood sample, extracted from human remains dated to nearly 5,000 years ago, was expected to confirm what scientists already believed, that ancient humans were biologically similar to us, just living in a different time. But when the analysis came back, the data didn't align with any known human blood profile. Not partially. Not approximately. Completely. At first, the assumption was simple: contamination. That's the most common explanation in cases like this. Ancient samples are fragile, easily altered by environmental exposure, microbial activity, or even modern handling. But the deeper the researchers looked, the harder it became to dismiss what they were seeing. Because the anomaly wasn't random. It was structured, consistent, reproducible. And that's where the problem began. The sample itself came from a burial site that had already been studied for years. It wasn't a newly discovered location, nor was it considered unusual in any significant way. The remains belonged to what archaeologists had classified as a typical human settlement from that era: tools, artifacts, burial patterns, all fitting within established historical frameworks. Nothing about the site suggested anything out of the ordinary. Which is exactly why the blood result was so unsettling. If the context was normal, the biology should have been too. But it wasn't. And that contradiction forced researchers to reconsider something fundamental. What if the context isn't as complete as we think it is? Blood, unlike bone, rarely survives over such long periods. It degrades quickly, breaking down into components that are difficult to analyze after thousands of years. But under specific conditions, low oxygen, stable temperature, mineral-rich environments, traces can remain preserved at a molecular level. That's what made this discovery possible. Scientists weren't looking at liquid blood, but at preserved proteins and genetic fragments embedded within the remains. These fragments can still carry identifying markers. Enough to reconstruct certain biological characteristics. And that's exactly what they attempted to do. They expected to find familiar patterns: ABO blood group indicators, protein structures consistent with Homo sapiens. Instead, they found irregularities that didn't fit within any standard classification. At first, the irregularities seemed minor. Slight deviations in protein structure. Unusual binding behavior. But when these variations were mapped out and compared against modern and ancient databases, a pattern emerged. The markers didn't match any known human blood group system. Not A, not B, not AB, not O. Even rare subtypes didn't align. It was as if this blood operated under a slightly different biological system, similar enough to be recognized as human, but different enough to resist classification. This wasn't just variation. It was divergence. Naturally, the first explanation was mutation. Genetic mutations occur all the time. Some are insignificant, others lead to noticeable traits. In rare cases, mutations can affect blood properties. But mutations usually occur within a known framework. They modify existing systems rather than creating entirely new ones. What researchers were seeing here didn't behave like a mutation. It behaved like an alternative configuration. Something that followed its own internal logic. To test this further, multiple independent labs were brought in to analyze the same sample. The idea was simple: if this was contamination or error, the results would vary. But they didn't. Each lab, using different methods and equipment, arrived at nearly identical conclusions. The anomaly was real. And more importantly, it was stable. That meant whatever this was, it wasn't a one-time irregularity. It was a biological state that existed, at least in this individual, in a consistent and measurable way. This is where the mystery deepened. Because if this blood type existed 5,000 years ago, where did it go? Blood types don't just disappear without leaving a trace. They spread, they mix, they persist in populations over time. Even rare variants tend to show up in genetic studies if they were ever widely present. But there was no record of this one. No modern equivalent. No historical reference. It was as if this biological trait appeared briefly, and then vanished completely. At this point, researchers began to explore a more complex possibility. What if this wasn't just an isolated mutation, but evidence of a population that no longer exists? Not a different species, not something entirely separate, but a subgroup of humans with distinct biological characteristics that didn't survive into the present. Human history is filled with examples of populations that rose and disappeared, sometimes due to environmental changes, sometimes through assimilation, sometimes for reasons we still don't fully understand. If this blood type belonged to such a group, it's possible that it simply faded out of existence, leaving behind only fragments like this one. But there was a complication. When scientists attempted to extract and analyze genetic material associated with the blood proteins, they encountered sequences that didn't fully align with known human DNA patterns. Not drastically different, but enough to raise questions. Certain markers were missing. Others appeared in unexpected configurations. It wasn't enough to classify this as non-human, but it also wasn't enough to comfortably call it typical Homo sapiens. It existed in a kind of gray area. Familiar, but not fully recognizable. This opened the door to competing interpretations. One theory suggested that we are looking at a lost genetic variation, something that existed within early human populations but was gradually eliminated over time through natural selection. Another proposed that this could be evidence of interbreeding with an unknown or poorly understood hominin group, resulting in temporary genetic traits that didn't persist. And then there was a more cautious perspective that our current classification systems are simply too limited, and that what we're seeing is not something unknown, but something we haven't yet learned how to categorize. The turning point came when researchers shifted their focus from classification to function. Instead of asking what this blood was, they began asking how it behaved. Preliminary biochemical analysis suggested that the oxygen binding capacity of the proteins might differ slightly from modern human blood. Not dramatically, but enough to suggest potential physiological differences. If true, this could mean that individuals with this blood type were adapted to slightly different environmental conditions, perhaps higher altitudes, different atmospheric compositions, or unique dietary factors. It's a subtle detail, but it changes the narrative. Because now, this isn't just about what was different. It's about why it was different. Imagine living in an environment where your body evolves, even slightly, to optimize survival under specific conditions. Over generations, these small changes accumulate, creating a biological profile that fits that environment perfectly. But if those conditions change, or if the population migrates, mixes, or disappears, those traits can be lost. Not because they were flawed, but because they were no longer necessary. In that sense, this blood type might not be an anomaly at all. It might be a remnant of adaptation, a biological echo of a world that no longer exists in the same way. I remember reading about how even today, certain human populations have unique adaptations, like the ability to process oxygen more efficiently at high altitudes, or resistance to specific diseases. These traits are real, measurable, and tied directly to environment and history. Now imagine discovering a version of that, frozen in time, preserved for thousands of years, but with no living descendants to explain it. That's what makes this case so compelling. It's not just different. It's disconnected. And maybe that's the most unsettling part. Not that something unusual existed in the past, but that it existed without a clear link to the present. We like to think of human history as continuous, as something that flows logically from one generation to the next. But discoveries like this suggest that the flow isn't always smooth. Sometimes, it breaks. Sometimes, entire variations of humanity appear, and then quietly disappear. The question is not just what this blood was. The question is why we've never seen it again. And more importantly, what else might we have already missed without realizing it? I'm going to continue exactly from where the last line left off, and this time I'll go deeper, slower, and longer, keeping everything in one continuous flow so it feels like a real documentary narrative. And more importantly, what else might we have already missed without realizing it? That question didn't just stay inside the lab. It followed the researchers into every new test, every comparison, every attempt to explain the anomaly in a way that felt complete. Because once you accept that a biological system existed which doesn't fit into modern classification, you are forced to confront a much larger uncertainty. Not just about one sample, but about the reliability of the frameworks we use to understand the past. Science depends on patterns, on repetition, on the idea that if something is real, it will appear again. But what happens when something is real, and doesn't repeat in ways we expect? The next phase of the investigation moved beyond the original site. If this blood profile existed once, there was a possibility, however small, that traces of it might exist elsewhere, hidden inside previously collected samples that had never been analyzed at this level of detail. Museums, research archives, and university collections around the world hold thousands of biological remnants from ancient human remains. Most of them were studied using older methods, limited by the technology of their time. Now, with more advanced tools, those same samples could reveal information that had always been there but was never seen. So researchers began requesting access, re-examining fragments that had been catalogued and stored away for decades. What they found wasn't immediate confirmation. It was something more subtle. In a few rare cases, scattered across different regions, there were faint irregularities. Small deviations in protein markers, slight inconsistencies in genetic fragments that resembled parts of the anomaly seen in the original blood sample. On their own, these irregularities had been dismissed as noise, experimental error, or natural variation. But when viewed together, with the new discovery as a reference point, they began to form a pattern. Not a strong one, not a complete one, but enough to suggest that this wasn't an isolated event. It had happened before. Quietly. Rarely. And almost always unnoticed. This changed the tone of the investigation. Because now, the question was no longer what is this, but how long has this been overlooked? And that question is far more difficult to answer. It implies that our understanding of human biology, especially in ancient contexts, may be shaped as much by what we fail to recognize as by what we successfully identify. The anomaly wasn't just in the blood. It was in the system used to study it. At the same time, another team focused on reconstructing the possible environmental conditions surrounding the original individual. Using geological data, climate models, and chemical signatures extracted from the remains, they attempted to build a picture of the world this person lived in. The results suggested a landscape that was familiar, but not identical to what exists today. Slightly different atmospheric composition, subtle variations in available nutrients, possibly even differences in microbial ecosystems. None of these factors alone would seem significant. But together, they create an environment that is not perfectly comparable to our own. And this is where a more complex idea began to take shape. What if the anomaly in the blood wasn't just genetic, but relational? Not something that existed independently, but something that only made sense within a specific interaction between biology and environment. In other words, the blood wasn't just different, it was tuned. Adapted in a way that only functioned fully under certain conditions. Remove those conditions, and the trait either disappears or becomes undetectable. This would explain why it doesn't appear in modern populations. Not because it was lost, but because the context that supported it no longer exists. To test this, researchers simulated certain environmental variables in controlled settings, analyzing how similar protein structures behave under different conditions. The results were inconclusive, but suggestive. Under specific chemical environments, certain unusual behaviors in blood proteins became more stable, more pronounced. It wasn't proof, but it pointed in a direction. A direction that doesn't rely on unknown species or extreme mutations, but on something more subtle, the idea that human biology is more flexible than we assume, capable of expressing different configurations depending on context. But even this explanation didn't fully resolve the mystery. Because it still left one critical detail unanswered. If this was a stable, functional biological state, why is there no clear evolutionary pathway leading to or from it? Adaptations usually leave traces. Transitional forms. Gradual shifts. But here, the trail seemed to begin and end abruptly. which led to a more uncomfortable possibility that some adaptations are not part of long-term evolutionary paths, but short-term responses. Temporary solutions to temporary conditions. They appear when needed, and disappear when they're not. If that's true, then the human story becomes far less linear than we imagine. Instead of a steady progression, it becomes something more dynamic. Fluctuating. Responsive. Shaped not just by time, but by moments. And in those moments, different versions of humanity might have existed, subtly different, biologically distinct in ways we are only beginning to detect. There's also a human side to this that often gets overlooked. When we talk about ancient remains, it's easy to reduce them to data points, samples, sequences, markers. But this was a person. Someone who lived, moved, experienced the world in a body that functioned slightly differently from ours. Not dramatically. Not visibly. But enough that, thousands of years later, it still resists our attempts to categorize it. Imagine living your entire life without knowing that your biology doesn't quite match what will one day be considered normal. And then imagine that everything about your existence, your environment, your community, your physical traits, disappears so completely that the only trace left is a fragment of your blood, studied in a lab that can't fully explain it. That perspective changes the nature of the mystery. It's no longer just scientific. It becomes existential. Because it forces us to reconsider what we mean when we say human. We tend to think of it as a fixed category, something clearly defined. But discoveries like this suggest that it may be more flexible, more variable than we are comfortable admitting. Not in extreme, obvious ways, but in subtle, measurable differences that challenge our definitions. And perhaps the most important realization is this. The anomaly doesn't prove that something extraordinary existed. It proves that our understanding is incomplete. That there are layers of human history, biological, environmental, genetic, that we haven't fully uncovered yet. And some of those layers may never be fully recovered. They exist only in fragments, in anomalies, in pieces of evidence that don't quite fit but refuse to disappear. So the mystery remains. Not because we lack data, but because the data leads us to questions that don't have simple answers. What we found in that 5,000-year-old blood sample isn't just a deviation from the norm. It's a reminder that the norm itself may be narrower than reality. That human history might include variations we haven't accounted for, adaptations we don't recognize, and biological states that existed quietly, briefly, and then vanished without a clear trace. And if something as fundamental as blood, something we consider basic, universal, can hold a mystery like this, then it raises a final, unsettling thought. How many other parts of our biology carry histories we haven't yet learned how to read? How many answers are already in front of us, waiting for the right question to reveal them? Because sometimes, the most important discoveries are not the ones that give us clarity, but the ones that make the world feel a little less certain than it did before. If you want to explore more stories like this, where science meets the unknown, and simple discoveries turn into deeper questions, make sure to like the video, subscribe to the channel, and share your thoughts below.